Hello and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Rebecca, lead tutor for biology and chemistry. In today's video, we will explore how to predict polar and nonpolar compounds using their molecular shapes. Let's get started. In the first video, we defined polar and nonpolar molecules. A polar molecule occurs when there is unequal sharing of electrons in a bond. This occurs when one element forming a bond is more electronegative than the other. The more electronegative atom, which is chlorine in this example, will have a partial negative charge because the electrons are more attracted to it, while the less electronegative atom, hydrogen, will have a partial positive charge. When one side of the bond is more electron dense than the other, the dipole moment will be represented as an arrow pointing towards the more electronegative atom, chlorine, and the plus end of the arrow will be on the less electronegative atom, hydrogen. A nonpolar molecule occurs when there is equal sharing of electrons within a bond. This is because both elements have equal electronegativity. Some compounds that have polar bonds but may still be considered a nonpolar compound. This happens when the dipole moments with equal magnitude but opposite direction cancel each other out. Now let's look at the Vesper shapes, which stands for the valence shell electron pair repulsion shapes, and how molecular shapes affect polarity in compounds. It is essential to know the difference between electron structures and molecular shapes, structures, or geometry when studying the Vesper theory. The electron structures refer to the arrangement of electron groups around the central atom, while the molecular geometry illustrates the arrangement of atoms or elements around the central atom. The electron structure and molecular shapes share some common names, especially when there are no lone pairs of electrons around the central atom. In the presence of lone pairs on the central atom, the molecular shape will have a different name from the electron structure. Generally, the dipole moments of molecules that don't have lone pairs on the central atom will cancel each other out as long as the terminal atoms are identical. These types of compounds have a symmetrical distribution of charge, so they are nonpolar. Notice that since there are no lone pairs on the central atom, the electron and molecular structures have identical names. This table shows a summary of nonpolar molecular shapes, namely linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. There are two exceptions where a symmetrical distribution of charge is retained in the presence of lone pairs on the central atom that is bonding to identical terminal atoms. The first is seen in the trigonal bipyramidal electron structure, when there are three lone pairs on the central atom, causing a linear molecular shape in the compound. This way, the dipole moment cancels out since the terminal atoms are identical and the bonds are in opposite direction of each other, making the whole compound nonpolar. The second exception is in the octahedral electron structure, where the central atom has two lone pairs that causes the molecular shape to be square planar. Such a shape has a symmetrical distribution of charge, resulting in zero net dipole moment, as all bonds have equal magnitude and are pointing in opposite directions of each other. Hence, the compounds with square planar geometry are nonpolar. Now I'll go over the entire Vesper chart and we'll go through each electron structure and molecular structure one by one. The first electron structure is linear. This can only exhibit a linear molecular shape. As I explained earlier, there is a symmetrical distribution of charge in this shape as the compound with this geometry is nonpolar. Beryllium hydride is a good example for this, since the central atom beryllium bonds all of its valence electrons equally to two hydrogen atoms. The second electron structure is trigonal planar. It can have two variations of molecular shapes depending on the presence of lone pairs on the central atom and the number of bonds that it's forming. The molecular geometry can be trigonal planar or bent. If the central atom is fully bonded to three identical atoms, such as in boron trichloride, then the molecular structure is a trigonal planar, which is the same name as the electron structure, and it is nonpolar due to the symmetric charge distribution. On the other hand, if the central atom is only bonded to two other atoms and has a lone pair on the central atom, then the molecular structure will be bent. This structure does not have a symmetrical distribution of charge and has a non-zero net dipole moment. Thus, this compound is polar. For example, sulfur dioxide has a central atom, sulfur, bonded to two identical atoms, oxygen. Sulfur has a lone pair since it does not bond all 6 of its valence electrons. Due to the bent molecular structure, the dipole moments of the bonds do not cancel each other out, therefore this compound is polar. If a central atom with a tetrahedral electron structure has bonded all its valence electrons to 4 other identical terminal atoms, as in the example methane, the molecular shape is also tetrahedral. As mentioned before, this kind of compound is nonpolar. If the central atom is bonded to only 3 other atoms and has 1 lone pair of electrons, then the molecular structure of the compound is trigonal pyramidal. This structure is not symmetrical and will result in a non-zero net dipole moment. For example, in ammonia, since the valence electrons of nitrogen amounts to 5, it will be left with 1 lone pair on the nitrogen after the central atom bonds to 3 hydrogens. Due to the presence of the lone pair on the central atom, this structure will not have a symmetrical distribution of charge, making it a polar compound. In compounds such as water, where the central atom has 2 lone pairs of electrons and bonds to 2 identical terminal atoms, the molecular structure is bent. There will be a non-zero net dipole moment, so the compound is polar. Trigonal bipyramidal electron structures can have 4 types of molecular shapes. The first is trigonal bipyramidal shape, in which the central atom has a total of 5 valence electrons, and it uses all of them to bond with 5 identical terminal atoms. Compounds like phosphorus pentachloride that exhibit this molecular shape are nonpolar. Seesaw shapes occur when the central atom bonds to 4 identical terminal atoms and has 1 lone pair left. This shape has an asymmetrical distribution of charges, so it is polar. A good example is sulfur tetrafluoride. T-shaped compounds are the result of trigonal bipyramidal electron structures having 3 bonds and 2 lone pairs. Compounds with this shape, like iodine trichloride, are polar. The last kind of shape this type of electron structure can have is a linear geometry, which is one of the exceptions where we find an asymmetrically distributed charge in the presence of lone pairs on the central atom. Compounds like xenon fluoride exhibit this shape and are nonpolar. Lastly, let's take a look at the various molecular shapes an octahedral electron structure can have. If the central atom has a total of 6 valence electrons and used all of them to form bonds with identical terminal atoms, the molecular shape of the compound is called octahedral. And as we saw earlier in this video, compounds with this molecular geometry are nonpolar because they have a symmetric distribution of charges. Sulfur hexafluoride is a good example for this. If only 5 of the electrons are bonded and 1 lone pair is left on the central atom, as seen in bromine of pentafluoride, the compound will have a square pyramidal shape, rendering it an asymmetrical distribution of charges, which makes it polar. Finally, when there are 4 bonds formed and 2 lone pairs left on the central atom, in compounds like xenon tetrafluoride, the shape will be a square planar. This is the second instance where we see dipole moments of the bonds canceling each other out, even though there are lone pairs on the central atom. The whole compound is therefore nonpolar. Thank you for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center and follow us on social media. See you next time.